I'm pretty sure all people aren't going to want to watch it.
All right, so we're going to look at 22-1 similar right triangles. Our learning goals for today: find ratios of side lengths in similar right triangles. Give an acute angle of a right triangle. Given the acute angle of a right triangle, identify the opposite leg and adjacent leg. So we have Trisha is a commercial artist working for the Right Angle Company. The company specializes in small business public relations. Trisha creates appealing logos for client companies. In fact, she helped create the logo for her company. The Right Angle Company will use its logo in different sizes for stationery letterhead, business cards, and magazine advertisements. The advertisement and stationery letterhead size logos are shown below. So we have the magazine advertising size logos and then the stationery letterhead logo size. So what observations can you make about these triangles? Bless you.
They're right triangles.
They're both right triangles. They are similar. How would you how do we know that they're similar?
Because they both say the right.
All right, so they have
right triangles.
all right, so in order to be similar, what has to be true about the corresponding parts? The angles all have to be congruent. So the corresponding angles have to be congruent. This is our right angle, so that means that this angle and this angle have to be congruent, and then this angle and this angle have to be congruent. What do we know about the corresponding sides? Obviously, the sides aren't equal, but they're going to be proportional. All right. And so, these look similar. In order to prove that they were similar, what would we have to do to the sides? We have to set up what? Well, we would have to set up the ratio, the proportions, to show that corresponding sides were in fact proportional. All right, so are all right triangles proportional? Are all right triangles similar? So on Friday, we looked at a 45-45, so it was an isosceles right triangle, but we also looked at a 30-60-90. They're both right triangles, but are they similar? No. Corresponding sides are not proportional. And corresponding angles, are corresponding angles congruent? No. This angle's 45, this one's 60. This angle's 45, this one's 30. So do they meet the similarity criteria? No. All right, so measure the two angles, measure the two acute angles and lengths of the sides of each logo. And so we're going to determine, they look similar, we're going to determine if they actually. Let's see how we are. So although the measurements can never be exact, the lengths of the sides of any right triangle satisfy the Pythagorean theorem. Confirm that the Pythagorean theorem is satisfied. So just take a couple seconds and do these satisfy. So it's 3 and 1, so 3.25 squared. That equals 10.5625. Does that equal 3 squared plus 1 1/4 squared? Yeah, my calculator matches, right? So now let's take 1.5 squared. Does that equal our 2 legs squared? All right, so the numbers that I'm getting for the second one don't quite match up. Because for 1.5 squared, I get.
Don't you have answers?
Yeah, back there. So let's look at these measurements again. I think this one seems a little bit long.
I'll try and see if they're right in the center of this.
All right, so rounding to tenths, does it match? Do we have equal sides? Yeah, so it checks out, and we're good, right? All right. So when in doubt, round to your benefit. All right. So all right. So although the measurements can never be exact, the lengths of the sides of any rectangle satisfied the Pythagorean theorem. Confirm that the Pythagorean theorem is satisfied by the measurements of the two right triangle logos. So we showed our work.
Oh, yeah.
So 2.3 equals 2.3. And so what was the other one? The other one worked out nicer. The numbers anyway. The logos are similar triangles. Justify the statement, then give the scale factor of advertising logo lengths to corresponding letterhead. So what were our side lengths for the advertising logo, the big one?
Hypotenuse is 3.25. The long leg is 3 inches. The shorter leg is 1.25 inches.
And then for the
I don't break down the small.
and then for the small ones, our hypotenuse was 1.5, right?
Yeah. Yes. There's a line through those. And then it was 5 eggs.
All right, so to get from 3.25, to get from 1.5 to 3.25, to get from our letterhead to our advertising, what do we multiply by? Or like if we set these up as fractions, I guess. So you said 2.3? Okay. So is it the same from here to here?
Yeah.
And then from 5/8 to 1/4?
Oh, 10
I know, half over. So would we call that number that can get us from one triangle to the other for all our side lines? But in
Are you scale factor?
scale factor. So what's our scale factor?
2.3. Oh. Are you still recording?
I think so. Yeah.
Hey guys.
All right. What did we say it was? So 1.5 divided by. So I have 0.46 as one scale factor. And what am I doing when I multiply by this number? And then I also had 2.17. So when I use the scale factor 2.17, I'm going from which triangle to which triangle? When I'm using this 2.17?
No, those small ones are big.
So this is using small to big, and then 0.46 is big to small. So just refreshing our scale factor stuff. The triangular logo used on the right angle company business cards is also similar to the logos used for advertisements and letterheads. The scale factor of letterhead logo lengths to corresponding business card length is 231. Determine the length of each side of the business card logo. So they're saying 2.3 to 1. So from letterhead to business card, we have a logo of 2.3 to 1. So if we know the letterhead, so can we find the business card triangle? Yeah, what are we going to do to each of the sides? Are we getting bigger or smaller? Okay, and what's our scale factor for this one? Are we getting bigger or smaller? So be careful here. From letterhead to business card. Smaller, because we're going from a sheet of paper to a little business card, right? So we want to get even smaller. By how much smaller are we getting? But we want to get smaller, and 2.3 as a scale factor tells us to do what? So if we do negative, what's going to happen to our image? Think about on our, if we're on a coordinate grid, if we add a negative in front, what does that do? It flips it. So we don't want to flip it, but we want to get smaller. What does our scale factor have to be in order to get smaller? It needs to be a fraction. So what's our fraction? So to get from business card to logo, what do we multiply by?
2.3.
2.3, right? So if we multiply by 2.3 to get from business card to letterhead, to go from letterhead to business card, what are we going to do? Divide by 2.3. And when we have a fraction, what goes in our numerator here?
You're
1. So it's like multiplying by 1 over 2.3. Right? We can convert that. If you don't like the decimal and the fraction, which technically is essentially, it's like saying ain't in English class. Probably not a word that you use frequently in front of Miss Britson.
It goes up 10 over 23.
All right, so this is 10 over 23. Or 8. This we don't mix in math proper methods. We don't combine fractions and decimals. So we can write it as a fraction as 10 over 23. Or Garrett, what did you say the decimal was?
0.43.
All right, we multiply by the decimal scale factor. All right, use a ruler to draw the business card located to scale in the space below. So all right, so what are my sidelines? So we know the letterhead dimensions because we got those, right? So what's my dimension for, what's my small side for the dimension of the business card? Was it 5/8? I'm asking.
Yeah. Yeah. Your small size business card.
Okay, so if the letterhead has a small side of 5/8, what's the dimension on the business card?
10 by 0.43.
Yep. So we're going to take 5/8 and then multiply by.
It's going to be 0.26 or 43 over 1/6.
Okay, I used the exact measurements in scale factor and I got 0.27. As a fraction, it's 25/92. All right, and for our long leg, we had 1 3/8. Is that correct? And we're going to multiply by our scale factor. And I have 55/92. And then what is our hypotenuse? It was 1.5, correct? So 15/23. All right, questions on where those numbers came from? Okay. Trisha tries to incorporate a right triangle into many of the logos she designs for her clients. As she does, Trisha becomes aware of a relationship that exists between the measure of the acute angles and the ratio of the lengths of the sides of the right triangles. Use each grid below to draw a right triangle that has a longer vertical leg of L units and a shorter horizontal leg of S units. The first triangle is drawn for you. Use the Pythagorean theorem to find the length h of the resulting hypotenuse to the nearest tenth. Record its length in the appropriate place on the bottom of the grid. So this is telling us our long leg is 5 and our short leg is 4. So when we're drawing this, we're going to go up 5. 1, 2, 3, 4, 5. And we're going to go out for this way, so use Pythagorean theorem to find out what our hypotenuse is. So what's the Pythagorean theorem again, just in case we forgot? All right, so what is our A in this one? All right, so that equals c squared. So we have 25 plus 16. So 25 plus 16.
It's 41.
So we got 41. So square root of 41. Just leave it. So c equals square root of 41. Oh, we need this one. What's that? They've already drawn that for us. So we have 8 squared plus 6 squared. So 8 squared plus 6 squared, so 64 plus 36. 100. So 100. So square root of 100 is 10. Alright, so I think you got for C, D, and E and F. Let's do those real quick. We'll take a minute and get those drawn and calculated. This might be one to divide and conquer with your neighbor. And so, all right, so number 6, some of the triangles in grid A or F are similar to each other. Identify how the groups of similar triangles using the grid number and explain how you know they are similar. So looking at these, which ones are similar triangles? So if we look at A and B, are they similar triangles? To get from 8 to 5 and 6 to 4, are we multiplying by the same thing? No. All right, so if we look at B and C, are they similar triangles? B and C? Are these similar? Then what's the scale factor to get from this triangle to this triangle? So to get from 5 to 4, what do we multiply by? And then from 4 to 3, is it the same thing? No. All right, what about from A to C? Are they similar? Are A and C similar?
Yes.
Yes. Yeah.
So like in group B, it has like the L equals 5, and that's like going up and down. Going up and down, and then the side or the S.
It doesn't. As long as you're long side, they can flip it. But does that change your hypotenuse? No, because your long side is still the same. It doesn't matter which way your long side is facing. No. So looking at these, are these two similar triangles?
Yeah.
Yes. So A and C are similar. And what's our scale factor? If we look from C to A, what would we multiply by? 2. Yeah. And then from A to C, 0.5. Alright, so looking at D. What that triangle is similar to what triangles? Alright, so 8 times what gets us 10, and then is 6 times 8 the same thing? B and D are similar, multiplying by 2 or half. Alright, so what else? What about E and F?
No, because both of them.
No, just 2 because that's Yep. F. So here our short sides are the same, so that's not it. What about A and E? So we have 8 times.
C and E.
So we have C and E. C and E. So 4 times 3, yeah, so C and E has a scale factor of 3, right? So 4 times 3 is 12. 3 times 9 is, 3 times 3 is 9. And then these two are similar. If we set up 8 over 12, does that equal 6 over 9?
Yeah.
Yep, 1.5. So A and E. It sure is. And what do we say? C and E. Any other ones where we set up when we have, let's see, we said E and F. No, what did we say? E. No. D and F. So if you set up is if 10 over 6, is that the same as 8 over 3? No, I got 1.6 and 2.6 for D and E, so they're not similar. I think that's good. Not those two. 5 over 4 and 4 over 3. No, I think that's it. All right, so setting up, so we have our combinations there. If A and C, nope, we got it. So A and C, and then A and E, and then C and E. All right, so we're good there. So for triangle, for angle C, side AR is the opposite, and side RC is the adjacent leg. For angle A, side RC is the opposite leg, and side AR is the adjacent leg. The adjacent leg is holding hands with the angle. So we have angle A here. It is holding hands with the adjacent side. The hypotenuse is never your adjacent side. So your hypotenuse is always right across from your 90 degrees. So 90 degrees, there's your hypotenuse, always. So angle A, it's holding hands with its adjacent side. So the adjacent side is AR. And across the way is the opposite. They can wave at it because it's opposite the triangle. So the opposite side is CR. If we're looking at angle C, it's holding hands with its adjacent side. So what's its adjacent side? RA. No, it's adjacent side. So at angle C, CR. So it's holding hands with CR. Here's angle C. The adjacent side is the one it's making up half of the angle. So angle C is holding hands with side CR. And that's what actually makes that angle up. And then it's waving across the way to the opposite side. So the opposite side is RA. So we're okay with those because they're going to be super important for the next 2 weeks. All right. So in right triangle bus, identify the opposite leg and adjacent leg for angle U. So angle U is here. So what side is angle U holding hands with?
US.
US. So the adjacent leg is US. And what's the opposite leg? Who is angle U waving to? It is waving to SB. All right, no questions there. All right.